So in the first section of our trigonometry class, we're going to want to take a look at a review of real numbers and their properties. So most of this section is going to be review, and we're going to want to make sure that you get started on the right foot in terms of accessing the information that you learned in Algebra 1 and Algebra 2 and bringing that to play as we continue on studying trigonometry. So what we're going to be doing in this section 1.1 is we're going to be going back through how we represent and classify real numbers, how do we order the values of real numbers, and how do we use inequalities, how do we find the absolute values of real numbers and the distance between two real numbers, how do we evaluate algebraic expressions, and how do we use the basic rules and properties of algebra. So this may be a little bit of a lengthy section, but we're going to go through this relatively rapidly. So when you think about real numbers have a number of different subsets. So generically, real numbers initially can be split off into irrational numbers and rational numbers. And now irrational numbers are numbers that cannot be represented as a ratio between two other numbers. So for instance, rational numbers can be represented as a ratio. For instance, 1/2 is a rational number. An irrational number would be something like the square root of 2. I can't express this accurately as a fraction. Okay, so irrational numbers tend to be square roots of prime numbers. They tend to be the number like pi or Euler's number. Rational numbers are all numbers that could be expressed somehow as a ratio between two numbers, including some of these other numbers like natural numbers, 1, 2, 3, 4. Whole numbers, the difference between whole numbers and natural numbers is you add in 0. And then when you move on, the difference between integers and whole numbers is you add in the set of negative numbers. So these are all rational numbers. So we've talked about integers here are the numbers that we think about, -1, -2, -3, 1, 2, 3, 4. And then we have non-integer fractions like 1/2, and they could be positive or negative, -1/2, right? And we have negative integers, we have whole numbers, we have natural numbers, and we have 0. So I talked about natural numbers, whole numbers, integers, and then 0 is part of this set of integers, and it's also sort of a special entity unto itself. Okay, so this is just getting back through things that you should already know. And when we start talking about classifying numbers, when you look at things like, what are these things? Natural numbers, whole numbers, integers, rational numbers. Well, -13, right? It's not natural, it's not a whole number because those don't include negative numbers, but it is an integer. So -13 is an integer, right? When we look at the opposite of the square root of 5. Well, the square root of 5 is an irrational number. That's E. If we look at -1, -1 is, again, it's an integer. That would be C. When we look at -1/3, right? That's a rational number, right? Again, it's not like -13 or -1. They fit into smaller subsets, but it's a ratio of two numbers. It is a rational number. Right? When we look at 0, 0 is a special number, but it's also one of our integers. So that's C. 5/8, that's also a rational number. It's a ratio between two numbers. Right? So that's D. And square root of 2, that is an irrational number. Pi is an irrational number. Right? And again, we know it's an irrational number because it is a decimal that goes on forever without falling into a repeating pattern. So for instance, 1/3 is a decimal that goes on forever, but it falls into a repeating pattern. It's 0.33333333. So, whereas pi does not fall into a repeating pattern. Okay, 7 is a natural number. It's also a whole number, and it's also an integer, and it's also a rational number. So when you think of some of these things, if you go back to that chart, you can see that when rational numbers, well, integers are rational numbers, negative integers, whole numbers, natural numbers, zeros, these are all rational numbers, but they sometimes fit more specifically in one of these subsets of rational numbers. If I wanted to put points on a number line, we're talking about working with their generic values and understanding what's like what. And normally what you would do is you would put things into a common form. The thing that's challenging, perhaps, sometimes yes, sometimes no, is that we've got a mix of fractions and decimals. So it would make sense for me to put them all into the same form if I want to compare them and their relative values. So this would be -1 6/10, which would be 3/5. And this is 7/10, and that will help me a little bit. So when you start thinking, well, we'll go -1, -2, start putting some scale into our number line. And where do these things go? Well, 5 halves, that's 2 1/2, so that's all the way out here. Let's put 5 halves there. And then -1.6, well, that's -1 3/5, so it would be right around in here, -1 3/5, we'll call it about there. -3/4, that's going to be right about here. And all this stuff should be super, super familiar to you. And 7/10 would be right about there, 0.7. Right? So this was also -1.6. So one method, one strategy to help you is in putting them in order is put them all in the same form. You may or may not need that. Depends on how close to each other they are. Okay, if you move through, again, more of the same. If we wanted to go ahead and look at where do these items fall in the order on the number line, remember something is less than something else if it's to the left, it's more than something else if it's to the right. So if I'm going to relate -3 and 0, -3 is less than 0. -2 is greater than -4 because it's to the right on the number line. See, 1/4 and 1/3, well, 1/4 is less than 1/3. And D, -1/5 is greater than -1/2. Okay, so I didn't put these on a number line, but that would have been, again, another strategy by which you might have addressed this. Right? Really basic stuff that you should have known for a long time. All right, now this may be a little different. I mean, for me personally, and if you think about our Algebra 2 book, we haven't notated things in exactly this way. What they're using is they're using these types of brackets, either curved brackets or squared brackets, to talk about inclusion. And in other texts that we've worked with, we may have thought about those in terms of solid and closed dots. So for instance, this inclusive would have been a closed dot. In this textbook, they're going to use a bracket, a squared bracket. Whereas this one would have been open dots because it's not inclusive, right? So this would be for or equal to, gets a solid dot or a square bracket. Without the or equal to, it gets a curved bracket or parentheses, or it gets an open dot. I'm not going to hold you to using the book's nomenclature, but I do want you to understand it, right? And then you see they have a different notation here of putting two values with these specific brackets. And this could be very confusing, honestly, because you might confuse this for an ordered pair. So this is inclusive on the left, but not inclusive on the right. It would look like that. And this one was not inclusive on the left and inclusive on the right. And this might be more of what you're used to seeing. Okay, so these are bounded intervals. What that means by bounded is it has an end point on either end. So they have specific stopping places. Okay, and this is called a closed interval because it includes the ends. This is called an open interval because it doesn't include the ends. So this is all just vocabulary that this particular book uses. Right, now when you talk about unbounded intervals, right, you see these are all compound inequalities. But they were compound and inequalities. So in this case, it might have been read, A is less than or equal to X x is greater than or equal to a and less than or equal to b. X is greater than a and less than b. Whereas here, x is greater than or equal to a, that would be a closed dot on one side, and it's unbounded going to the right because it's greater than. X is greater than a would be an open dot, so greater than or equal to closed dot, simply greater than would be an open dot, or in this case, closed bracket, curved bracket. On this particular item, x is less than b, that's an open dot and it's unbounded to the left. Sorry, I skipped this one. X is less than or equal to b would be closed dot and unbounded to the left, or again, you can use the square bracket, curved bracket. And the entire line, x is greater than negative infinity and less than infinity would be the entire line. So if we go through practicing something like that, if we want to express this, for a, I want to show x is less than or equal to 2. So there's where 2 is, and I do a hard bracket, and it's less than, so it's moving in this direction. Equally, I might have done a closed dot and moving in that direction, same idea. And here, x is greater than or equal to negative 2, so let's do negative 2, or equal to would be a hard bracket or a closed dot. And it's less than 3, 1, 2, 3, so that would be an open dot or a curved bracket. All right, so that's in either of the forms, and by this I'm sure you know how to do these things. Okay, now they're doing a different type of notation, but they haven't really changed anything. If I wanted to express this on a number line, it's between -1 and 0. And I've got the curved brackets on either side, so I have curved brackets on either side. There's my line segment. Or I could do open dots on either end. In this case, I go from 2 to infinity, 1, 2. That means it's unbounded. It's inclusive on the left, and it's unbounded on the right. Or I might do a closed dot and off to the right. Okay, using inequalities, right, which we were already doing. If I wanted to go ahead and go through this, use the inequality notation, right? If we look at this, in the inequality, c is less than or equal to 2 can represent the statement, c is at most 2. And part of what we're trying to do here is we're trying to develop the language that is used, at most, is used in relation to, right, less than or equal to. So at most, the most it can be is 2, but it could be anything less than that. The specific language we use to do this is part of what mathematics literacy. Okay, so if we look at this one, all of the x's in the interval between, right, not including -3, but including 5. So between there, right, might be easier. Normally it is easier to represent these things graphically than it is to represent them in words. So if I want to use inequality notation to represent that x is greater than -2, so here's -2, x is greater than -2, and at most 4, that means it's less than or equal to 4. Okay, so I'm interpreting greater than and at most, and turning them into these signs, greater than, less than, or equal to. Right? When we start talking about absolute value, I know that the absolute value of a is equal to a if a is greater than or equal to 0, meaning a positive number. And it's equal to the opposite of a if a is less than 0, meaning a negative number. And of course, if it was 0, it would just be 0. Okay, so greater than or equal to 0. If we want to take a look at absolute values, in a, the absolute value of 1 is 1. In b, the opposite of the absolute value. So this is important. Absolute value in order of operations is basically going to function as parentheses. So I'm going to do it first. This minus sign on the outside, that is like multiplication by -1. So I'm going to do parentheses and then multiplication. So this will be the opposite of 3/4. When you talk about c, it's going to be 2 over the absolute value of negative 3. That becomes 2/3. And D, again, much like B, it's going to be, I'm going to take the absolute value first, which is 0.7, and I'm going to take the opposite of that, which is negative 0.7. So just because there's an absolute value doesn't necessarily mean the result ends up being positive. It depends on how order of operations plays out in your expression. If I wanted to evaluate an absolute value for numbers like this, right? For instance, if x is greater than negative 3, I would plug in negative 3 and think of that as a bounding limit, right? So if I plug in negative 3, the absolute value of negative 3 plus 3 over x plus 3, in this case, that would be 0, but x is going to get bigger from there. So as x gets bigger, my numerator will get bigger, and consequently the value of my fraction will get bigger. So in this particular case, in A, my lower limit is B is 0, but it's not going to be inclusive because we're saying greater than negative 3. So it would never get as far down as negative 3. So in this case, I know that for this value, for values where it is greater than negative 3, it's going to be non-inclusive of 0. Right? If I wanted to graph that, it's going to be non-inclusive of 0, and it's going to go on. Or I could do a bracket, and it's unbounded to the right. If we look for values that are less than negative 3, well, less than negative 3, when I use negative 3, it'll be 0, and anytime I now go lower and lower and lower from negative 3, this item here was going to become negative, but this is also going to become negative. So this will become negative, it'll be positive, the denominator will become negative, and what will happen is the opposite of what happened here. And that's that we'll have, curved bracket. I did a hard bracket there. A curved bracket here, and it's unbounded to the left. Open dot, open to the left. Okay, so when you're thinking about boundaries like this, you want to think about what does it happen at this boundary, and what happens as we move in this manner away from that boundary, meaning we go greater and greater and greater than negative 3. Okay, the law of trichotomy states that for any two numbers a and b, one of these, this sounds so like common sense, either they're equal, or a is less than b, or a is greater than b. Those are the only three outcomes that can happen. I think the mathematician who wrote the law of trichotomy is probably the mathematician that everybody makes fun of when they get together at parties, because this one sounds pretty obvious, but he's got a law. Right? So if we want, though, to put the correct sign in, the absolute value of negative 3 is 3. How does it relate to 4? Well, it's less than 4. The opposite of the absolute value of negative 4, so the absolute value of negative 4 is 4, and the opposite of that is negative 4, versus the opposite of the absolute value of 4, that's also negative 4, so those are equal. And the absolute value of negative 3 is 3, and the opposite of the absolute value of 3 is negative 3, so this would be greater than. Okay, so if you think through these things, it's not rocket science that we're doing here. We're really going back through some really basic algebra things that we should have already learned. So we've got some basic properties of absolute values, which I assume that you already know. One thing that may or may not have been explicitly told to you is that absolute values happen in order of operations where parentheses happen. So they happen first when you're doing PEMDAS. They happen first. And then we've got all these different rules of absolute values, and I think they're things you're all very familiar with. So I'm not going to read them out to you. You can print out the lecture slides if you want to have copies of these things. They're also in your book. But when we take a look at distance between 2 points in a number line, they're going to say if a and b are real numbers that are on a number line, the distance between them is the absolute value of their difference. And it doesn't matter which one I pick first. It doesn't make any difference. So I would say, in this case, the distance between 35 and 23? Well, it would be the absolute value of 35 minus negative 23, and that's going to be 58. Okay, between negative 35 and 23, it's the absolute value of negative 35 minus negative 23. So I got a little sloppy there. Negative 35 minus negative 23 is negative 12, and the absolute value of negative 12 is 12. Right? And the difference between 35 and 23, 35 minus 23 again is 12. The absolute value is 12. So this is really explicit. It's things that you've done before, probably counting on a number line initially and later sort of rationalizing things out. Distance, though, which is important for you to remember, the reason it's always expressed as the absolute value of a difference is that distance is always positive, right? Distance is not something that denotes directionality like negative or positive. It's always positive. We don't have negative distances. Okay, and that's why it's always in this absolute value. When we start talking about algebraic expressions, which is sort of the first thing you normally work with in algebra, you should have handled these now for years, they're composed of different things. And what things they're composed of, it's really important to be really explicit about what they are. This algebraic expression has two terms. The terms are 5x and negative 1/7. Right? You'll notice that the operation sign is part of the term behind it. Okay, so we have 5x, and in front of the 5x is inherently a positive. We don't write it because it's redundant. But if there was a negative, that would be part of it as well. And there are two coefficients, the 5 and negative 1/7. So you'll see that the operation sign also comes into play with the coefficient. It's really essential that you understand the difference between terms and other elements, such as factors, because it's related to what you can and cannot do. For instance, when I'm working with a fraction, I cannot ever cancel terms that are common to the numerator and the denominator. But I can cancel factors that are common to the numerator and the denominator, and we'll talk about factors in a little bit. So again, when we look at this, my terms are 2x squared, negative 6x, and 9, and my coefficients are 2, negative 6, and 9. So now if I want to jump down here and I want to do that with this particular expression, I have terms. My terms are negative 2x and 4. Those are my terms. And my coefficients are negative 2 and 4. Okay, it's just really important that you understand this. You need to know the difference between terms and factors. And you need to be able to identify coefficients because often we use the coefficients rather than the whole term. Okay, and if we want to evaluate, that basically just means plug in a supplied value of x. When x is equal to 0, I plug in 0 for x. 4 times 0 is 0, minus 5 is negative 5. You could also write this in function notation. You could say the function of 0 is equal to negative 5. Okay, basic rules of algebra. We've got a lot of them, so I'm just going to go through them rather quickly. I'm not going to try necessarily to explain them all. I have an assumption that you all already are familiar with these. You should print them out if you need them. Keep them handy for yourself. So we've got rules like the definitions of subtraction and division. You notice that the definition of subtraction is adding the opposite. That, by the way, is y. Subtraction and addition occupy the same location in order of operations. They're the same basic operation. And division is multiplying by a reciprocal. So division and multiplication share a slot in order of operations because they are inherently the same basic operation. We have some properties of 0. Anything added to 0 will be itself. Anything with 0 subtracted from it will be itself. Anything times 0 is equal to 0. Anytime I have 0 in the numerator of a fraction, it's equal to 0. And anytime I have 0 in the denominator of a fraction, it is undefined, right? It violates one of the basic rules of algebra. I can't have 0 in the denominator of a fraction and evaluate the result. Okay, some other rules. Again, I'm not going to explain them all. I just want to make sure you know they're here. They're present in your book. They're available to print from the slides online. The commutative property of addition, the commutative property of multiplication, the associative property of addition, the associative property of multiplication, the distributive property, additive identity, multiplicative identity, right? Identity means it doesn't change. If it's addition, I add 0, it stays itself. If it's multiplication, I multiply by 1 and it stays itself. Right? Additive inverse, if I add inverses, it equals 0. We use this a lot to create equivalent expressions as we solve problems. And a multiplicative inverse, if I multiply something by its reciprocal, that's going to equal 1. Okay, so these are all, again, should be very, very familiar. You will notice there is no commutative property of subtraction, and there's no commutative property of division. And the same with the associative properties. They don't necessarily remain the same. Okay, properties of negation and equality, right? How do things become negative? How do things become equal? These are all very basic. You should review them, but I'm not going to discuss them. Okay, properties and operations of fractions. It's really important that if you have any basic problems with fractions that we go through it, right? Because fractions, the ability to do fractions, fraction operations is really essential in doing higher level algebra, right? You're not going to get through a really solid pre-cal or algebra 2 class without knowing how to do fractions to some degree. Okay, so these basic skills, being able to add or subtract, multiply and divide, these things are really important. And things like this, right, like the adding and subtracting with like denominators, if I can turn this into this, that means I can also turn this into this. And you'll hear me talk about this as distributing the division, right? Changing it. If I go from here in that direction, I will often say, well, you need to distribute the division. Because if I have 2 items, just like if I have 2 items being multiplied, right? If I have b times a plus c, that's going to be b times a plus b times c. Equally, if I have a plus c divided by, I'm going to say b again, that's going to be a divided by b plus c divided by b. So if I have to multiply each term in the expression by the distributive property, equally I would have to divide each term in the expression also using the distributive property. Okay, we multiply fractions, we multiply numerators together and denominators together. And when we divide fractions, we invert and we multiply. So invert the second fraction. You notice it's the fraction that you're dividing by gets inverted, and then you multiply. Okay, so if we want to go through, I want to multiply these fractions. 3/5 times x over 6 would be numerator times numerator, 3x, over 5 times 6, which is 30. But in reality, what I would always suggest you do is that you simplify before you multiply. I know that 3 goes into 30 and leaves 10. This is x over 10. But if I simplify first, if I say this is 3/5 times x over 3 times 2, now 3 and 2 are factors of 6, and I can cancel factors. I talked about the fact that I can't cancel terms, but I can cancel factors. When you're multiplying fractions, you want to cancel the common factors first and then multiply the result. So x times 1 is x, 5 times 2 is 10. Then your fraction will already be simplified when you're done. If I want to add fractions, I need common denominators. I take a look at 10. This is very simple. 10 is 2 times 5. So the factors in my denominator are going to be 2 and 5. And then also this 5. So the common denominator will be 10. So I'll have x over 10 plus 2x over 5 times another fraction that equals 1 that introduces this 2 that was missing from this denominator. This factor was not present there. So then I have x over 10 plus 4x over 10. that becomes 5x over 10, and I can simplify that to be x over 2. Okay, things that, again, you should be really familiar with this type of process. Just to reiterate the things we've done in section 1, you should be able to describe how to represent and classify real numbers. You should be able to describe how to order real numbers and use inequalities. You should be able to state or calculate the absolute value of a real number. You should be able to explain how to evaluate an algebraic expression. You should be able to state and understand the rules and properties of algebra. Okay, that's what we worked on in this particular section.